Welcome everyone for this VLSI design lecture series. In today's lecture video, I'll be discussing about delay. The two most common metrics for a good chip design are speed and power. Delay and power are influenced as much as by the wires as by the transistors. Both wires as well as transistors plays a vital role which influences delay as well as power in an integrated circuit. Before getting into the details of this delay and then the topics which are present in this module, it's vital for us to understand the important definitions such as what is meant by propagation delay, what is meant by rise time, what is meant by fall time, what is edge rate, what is contamination delay time, etc. So all those definitions can be easily understood with the help of the waveform which is shown on the screen. The waveform which is shown on the screen is the input as well as output of CMOS inverter. Along x-axis, the first waveform, along x-axis we have considered time, along y-axis we have considered V input. In the second waveform, along x-axis we have considered time, along y-axis we have considered V out. As we already know, the logic of CMOS inverter, when the input is high, the output should be low. And when the input is low, the output should be high. But if we observe, when the input is becoming high, instantaneously we are not getting the output as zero. The output is not becoming low. It is taking certain amount of time for the logic level to shift from logic level high to logic level low. So that time is nothing but propagation delay time. So we can understand each and every delay in detail with the help of the waveform. First, let us focus upon propagation delay time, which is represented as TPD. So this propagation delay time is the maximum time from the input crossing 50% to the output crossing 50%. I'll repeat once more. Propagation delay time is the maximum time from the input crossing 50% to the output crossing 50%, which can be easily shown in this particular waveform. Somewhere at this particular point, if we observe, the input is crossing 50%. And somewhere at this particular point, the output is crossing 50%. So the propagation delay time is defined as the maximum time from the input crossing 50% to the output crossing 50%. So this is propagation delay time. And if we observe, we have written it as TPDF, propagation delay time for falling edge. So we always consider rising edge or falling edge with respect to output waveform. So with respect to the waveform which is shown here, this is the falling edge. Hence, they have considered the propagation delay here as falling edge propagation delay. Similarly, we have one more propagation delay here, TPDR. If we observe, it is the maximum time from the input crossing 50% to the output crossing 50%. So this particular propagation delay is called as rising edge propagation delay because here the output waveform is rising. This particular thing. So the propagation delay is the maximum time from the input crossing 50% to the output crossing 50%. Next, let us focus upon what is meant by rise time. Rise time is represented by the symbol TR, T subscript R. So rise time is the time taken for the waveform to rise from 20% to 80% of its steady state value. It is the time taken by the waveform to rise from 20% to 80% of its steady state value. So this can be understood with the help of a waveform. If we observe here, we have a rise time here. As the definition gives us, rise time is the time taken by the waveform to rise from 20% to 80% of its steady state value. That time is called as rise time. Similarly, we have to analyze one more time called as fall time, which is given by the symbol TF. Fall time is defined as the time taken by the waveform to fall from 80% to 20% of its steady state value. I'll repeat once more. Fall time is the time taken by the waveform to fall from 80% to 20% of its steady state value. In this particular waveform, if we observe, fall time is the time taken by the waveform to fall from 80% to 20% of its steady state value. 80% to 20% of its steady state value. Next, let us focus upon the definition called as edge rate. Edge rate is given with the symbol TRF. Average value of rise time and fall time is called as edge rate. It is just the average value of rise time as well as fall time. It is given by the formula TRF is equal to TR plus TF divided by 2. So these are some of the definitions which you need to understand before getting on to the actual topics. Next, let us focus upon what is meant by timing optimization. So before getting on to the details of this timing optimization, there are certain introductory topics which has to be discussed. So the propagation delay, which we have discussed, is usually the most relevant value of interest and is often simply called as delay. A timing analyzer computes the arrival time, that is the latest time at which each node in a block of logic will switch. The nodes are classified as inputs, outputs, and internal nodes. The user must specify the arrival time for each input and the time data is required at each output. We normally give a term called as slack. Slack is nothing but the difference between the required as well as arrival times. Positive slack means the circuit meets timing requirements. Negative slack means the circuit is not fast enough. So with this introductory concepts, let us move on to what is meant by timing optimization. So in most of the designs, there will be many logical paths that do not require any conscious effort when it comes to speed. These paths are already fast enough for the timing goals of the system. However, there will be a number of critical paths that limit the operating speed of the system and require attention to timing details. Those paths are called as critical paths. So normally the critical paths can be affected by 4 main levels. The first level is called as architectural level or micro-architectural level. The second level is called as logic level. The third level is called as circuit level. The fourth level is called as layout level. I'll repeat. The critical paths are affected by 4 main levels: architectural level, or it is also called as micro-architectural level, logic level, circuit level, and the layout level. So let us first focus upon architectural level or micro-architectural level. Most leverage is achieved with the good micro-architecture. That means if we have to get an efficient integrated circuit, we always go with micro-architecture. The architecture of the chip should be as small as possible. This requires a broad knowledge of both the algorithms that implement the function and the technology which is being targeted, such as how many gate delay fit in a clock cycle, how quickly memories are accessed, and how long signals take to propagate along the wire. So all these details will be analyzed in this particular level called as architectural level. So there we have to identify the critical path and sort it out. The next level of timing optimization comes under logic level. Trade-offs include types of functional blocks, the number of stages of gates in the clock cycle, etc. So all these things comes under logical level. And the third important level is the circuit level. Once the logical level has been selected, the delay can be tuned at the circuit level by choosing the transistor sizes or using other styles of CMOS logic. As we have already discussed in all our previous classes, there are many ways a circuit can be implemented. We can use a normal CMOS logic, which consists of a pull-up network and pull-down network, or we can use fast transistor logic, which just consists of either NMOS or PMOS, or we can consider a transmission gate. A transmission gate is nothing but a circuit or a device where PMOS as well as NMOS transistors are connected in parallel. And there are n number of ways of getting the function apart from CMOS logic. In this particular level called a circuit level, the design engineer or the designer will have provision to choose which CMOS logic to apply and what kind of technology we have to use, what should be the size of the transistor. So all these things, directly affect the critical path. And finally, layout level. The delay finally is dependent upon the layout level. The floor plan is of great importance because it determines the wire length that can reduce the delay. Good cell layouts can also reduce parasitic capacitance as well. So finally, this architectural level, logic level, circuit level, all these three finally stages to the layout level. In this layout level, the design engineer does a floor plan. In his floor plan, he or she will be concentrating upon the wire length, the transistors used, etc. All these things will be there. The floor plan is of great importance because it determines the wire length that can reduce the delay. Mainly delay is because of wires. If this wire length as well as transistor sizes are minimized, we can reduce the delay. This is what is called as timing optimization. A good cell layout will also reduce parasitic capacitance. As we have discussed in our previous lecture videos, I've told you that parasitic capacitance affects the performance by reducing the speed of the transistors, by reducing the speed of the integrated circuit. If we have to increase the performance or if we have to increase the speed of the integrated circuit, we have to definitely reduce the parasitic capacitances. So designing a proper layout will definitely help to reduce parasitic capacitances. So this is about timing optimization. I hope that you have understood. Thank you.